Good morning. Today we have two lectures on characterization of both biocomposites and bio-nanocomposites, and it is divided in two parts. The first one is the characterization of the grafting efficiency, because remember that many times it's necessary to modify the fibers or the nanoparticles to impart some hydrophobicity or other properties. And so, of course, it's important to know if the grafting was effective or not. And the second part would be on the characterization of biocomposites and bio-nanocomposites. So first, an important note. It's necessary to perform an extensive washing, extraction, and also solubilization, centrifugation. Should be performed before characterization, and the objective is to remove ungrafted species. So there are different techniques that can be used. So I will present only these techniques, but some other techniques can also be, it works? Yes, can also be used. So the first one is X-ray diffraction. So maybe it's difficult to understand how X-ray diffraction can give some information about grafting efficiency, but we'll see that in some cases it's possible. But it's important to perform X-ray diffraction just in order to check if we keep the integrity of the fiber or the nanoparticles, because the grafting has to be performed only on the surface of the particle. So it means that the core of the fiber or nanoparticle should remain intact. So X-ray diffraction, so it provides information on the structure and phase identification of crystalline material. You have here two X-ray diffraction patterns for cellulose. So cellulose from birch fibers or microcrystalline cellulose. And so, as you know, cellulose is semi-crystalline polymer, meaning that we have some crystalline peaks, and what is called an amorphous halo. In the case of native cellulose, cellulose 1, we have this main diffraction peak at this angle, and so it corresponds to this atomic plane. Usually, you know, for X-ray diffraction experiment, the copper K-alpha line is used, meaning that in the Bragg equation, this wavelength is used, and D corresponds to the spacing of diffracting planes. So it's important to check if we still have this diffraction peak after chemical modification or grafting. We can also determine the degree of crystallinity. In fact, it's not really a degree of crystallinity like it is determined by differential scanning calorimetry, but it's a crystallinity index. And for this, there are two methods. The Segal method, which is given by this equation. In this equation, I002 corresponds to the magnitude of this diffraction peak, which is the most intense, and IAM corresponds to the magnitude of the diffraction peak in this valley, which is associated to the amorphous domains. So this is the first method. There is another method that involves the deconvolution of crystalline peak from the amorphous halo. You can see in blue here the amorphous halo, and in green, the different diffraction peaks that have been identified. And then we can consider the area under the peaks that correspond to AC, so it is associated to the crystalline domains, and AA that correspond to the area under the blue halo. So both methods can be used. Usually it's easier to use the Segal method. It's also possible to determine the size of the chrysolite that can be impacted by the grafting. It can be determined using this Scherer equation in which lambda corresponds to the X-ray wavelength. Delta theta is the width at half the maximum intensity, and theta corresponds to the Bragg angle. So in some cases, it's possible to see new signal by X-ray diffraction, which is the case here. In this case, starch nanocrystals have been used, and two different molecules have been graphed. Sorry, I have to remember. Yes, stearat was graphed, and you can see that on the surface of starch, a long, relatively long aliphatic chain was graphed, and on the other side, another molecule was graphed, so it's polyethylene glycol methyl, I don't remember the E, polyethylene glycol methyl ethers, yes, sorry. So that consists in this molecule, and you can see that in this case we have some oxygen atoms in the graft chain, meaning that in this case we expect stronger interaction between the graft chain and the surface of the nanocrystals. Not in this case, because it's only carbon atoms. So what we can expect is this kind of thing. In the case of polyethylene glycol methyl ether, and because of the oxygen atom, we can have some chains that lie parallel to the surface of the nanocrystals because of good affinity. But in the case of the stearat, we should have a brush-like structure. And so when looking to the X-ray diffraction pattern of unmodified starch nanocrystals, B corresponds to polyethylene glycol modified or graft cellulose nanocrystals, so it's more or less the same signal. But in the case of stearic acid chloride graft starch nanocrystals, we can see some strong diffraction peaks. And these diffraction peaks correspond to polyethylene. Correspond to polyethylene because in this case, the graft chains are long enough to crystallize. This is another example which is similar, except that in this case, polycaprolactone with two different molecular weights have been grafted on the surface of either cellulose nanocrystals or starch nanocrystals. It was a grafting onto approach. And so we can see the X-ray diffraction pattern for the unmodified particle and for the particle modified with the two different polycaprolactone. In the case of cellulose nanocrystals, it's difficult to see any change. It's easier for starch nanocrystals because you can see that we have a new peak here around 21 degrees that correspond also to the crystalline structure of graft polycaprolactone chains. For cellulose, it's more difficult to see because you can see that we have a very strong peak here, and so it's difficult to dissociate the two peaks. Another technique to evaluate the grafting efficiency is to disperse the graft fibers or graft nanoparticles in organic solvents. So it's a weightability test. I will show you some example. In fact, when the fibers or nanoparticles are hydrophobic, they can be dispersed in apolar liquid medium. You have an example here where you have neat cellulose nanocrystals. 1 and 2 refer to the suspension immediately after stopping the steering agitation, and here it's 15 minutes later. So this is in toluene. Neat CNC, we can see a sedimentation, because of course cellulose nanocrystals are hydrophilic and toluene is hydrophobic. A physical mixture of polycaprolactone and cellulose nanocrystals. Again, we observe the sedimentation. And when the cellulose nanocrystals are grafted with polycaprolactone, we can see that the suspension remains stable. This is another example, very similar also with cellulose nanocrystals. In this case, it's in chloroform because PLA was graphed on the surface of cellulose nanocrystals. And so it was also just after stopping the stirring agitation, and so longer time, 72 hours. Again, we can see the sedimentation on unmodified nanocrystals in chloroform. For the physical mixture, we also observe this sedimentation, meaning that it is not due to the presence of AD-adsorbed polycaprolactone, but when considering the grafting of polycaprolactone, we can see that we have a stable suspension. This is another one which was a little bit different. In this case, starch nanocrystals have been used, and they have been grafted with ASA, alkenic succinic anhydride, and polyisocyanate. You have here a photo of a drop of an aqueous starch nanocrystal suspension in dichloromethane. No miscibility, so the starch nanocrystals remain in the aqueous phase. And here for these photos, you have two liquids, water and dichloromethane, which are not miscible. So the density of dichloromethane is higher, meaning that it is at the bottom of the flask. For unmodified starch nanocrystals, you can see that the nanoparticles are located in water, and after modification, they migrate to the dichloromethane phase. So contact angle measurement can be also used to check the efficiency of the grafting. So you probably know that contact angle measurement is used to determine the degree of hydrophilicity, hydrophobicity of the surface, and it is the angle at which a liquid-vapor interface meets a surface solid. So it is this angle after dropping a liquid droplet, usually water. In the case of unmodified cellulose, of course, water is hydrophilic, cellulose is hydrophilic. There are some good interactions, meaning that the contact angle is quite low. After chemical modification, so in this case with palmitoyl chloride, the nanoparticles becomes, or the particle becomes more hydrophobic, and we can see this increase in the contact angle. So it's, so these are some examples. We have seen this, I think it was yesterday, for cellulose nanocrystals and cellulose nanofibril. Contact angle is a function of time. Unmodified nanoparticles, and so you can see that cellulose nanofibrils are more hydrophobic than cellulose nanocrystals. We have here about 60 degrees, and here it's 45. The reason is the presence of residual hemicellulose and lignin on the surface of nanofibrils. And after modification with an isocyanate, we can see this increase in the contact angle. This is another example in which the cellulose nanocrystals interact with this cationic surfactant, cationic quaternary salt here, with a positive charge that can interact with the negative sulfate group from the surface. And again, we observe this increase in the contact angle. So it's possible to quantify this experiment also using, so there are different approaches, but for cellulose, usually the Owens-Wendt approach is used. It is used because the surface tension in this approach is divided into two terms. One term which is associated to the dispersive interaction, so typically van der Waals interaction, and one term which is associated to polar interactions between the liquid and the solid. We can determine the adhesion work between the liquid and the solid, so the dispersive and polar components of both the liquid and the solid are involved. We can also use the Young-Dupré equation, which is here. So theta is the contact angle gamma L is the surface tension of the liquid. And of course, we can identify these two equations. We can rearrange a little bit, so it is just divided by this term here. And then you can see that by plotting this parameter, which is known because, of course, we know the nature of the liquid which is used, so meaning that we know its surface tension, its dispersive component. We can experimentally determine the contact angle. So it is plotted as a function of this parameter. And we can see that in this case, or maybe it's on the previous slide. Ah, no, yes. Sorry, I didn't write it. But anyway, so we can plot this curve, and we obtain a straight line. And for this straight line, the slope is related to the polar component of the surface tension of the solid, that can be determined, of course, and the intercept is the dispersive component of the surface tension of the solid, meaning that we can obtain both the dispersive and the polar component of the surface tension of the solid. So it was done in this example. I already showed you this example. So cellulose nanocrystals that have been graphed with aliphatic chains with different lengths. So the contact angle has been determined using 3 different liquids. So in fact, the objective is to plot a straight line, meaning that 2 liquids are enough, but it's better to have 3, of course. And in each case, the contact angle has been determined, and from the previous development, the polar component and the dispersive component, as well as the total component of the surface tension of the solid have been determined. So you can see that by grafting this molecule on the surface of cellulose nanocrystals, there is a strong decrease in the polar component of the surface tension of the solid, which was, of course, expected. Fourier transform infrared spectroscopy can also be used. So it is based on atom vibration and rotation and used to detect the internal molecular structure. This is the same example as previously, the same samples, unmodified nanocrystals and nanocrystals modified with these 3 different molecules. Of course, we can observe characteristic bands of cellulose. I will not detail everything, but they are here. They are characteristic of cellulose. And after chemical grafting, it's possible to observe new peaks. So, of course, it depends on the nature of the graft molecule. But in this case, these new bands have been observed, which are located here and here. You can clearly see that there is no band for the unmodified nanocrystals, and we have some bands here. With infrared, it's difficult to codify the grafting, but at least we can have this information. Another thing is that you see this very broad peak, and you know that it is associated to hydrogen bond OH stretching. Of course, after chemical grafting, part of these hydroxyl groups are no more present because of the grafting, and so we observe a decrease in the magnitude of this bond. So elemental analysis can also be used. So it is used to quantify the mass fraction of carbon, hydrogen, oxygen, and other atoms. So it is based on atomic absorption of the investigate element. And this equation can be used to determine the degree of substitution. So there is a high density of hydroxyl groups on the surface of cellulose fibers or nanoparticles. And part of these hydroxyl groups are replaced, so it is referred to the degree of substitution. So I will not detail the different parameters in this equation, but always the same example. Elemental analysis has been performed for the same sample. You have the percentage of carbon, hydrogen, oxygen, and the degree of substitution determined from the previous equation. And of course, what is expected when grafting this aliphatic chain is that the percentage of oxygen decreases because oxygen is mainly present in cellulose. But the percentage of carbon atom should, of course, increase. X-ray photoelectron spectroscopy, XPS. This is an interesting technique to study the grafting efficiency of biocomposites because the depth of investigation is very low. So it's around 7 nanometers, meaning that it's really an investigation on the surface of the nanoparticle. So in this technique, photons of specific energy are used to excite the electronic states of atoms below the surface of the sample. Electrons ejected from the surface are energy filtered before the intensity for a defined energy is recorded by a detector. So, of course, for cellulose, we have mainly carbon and oxygen atom, and we observe this signal associated to oxygen and to carbon. This is called the general XPS spectra, and we have this different curve also associated to neat cellulose nanocrystals and modified cellulose nanocrystals. So usually, a zoom is made on this region to make a distinction of the carbon atom depending on their environment, which is reported here. So this C1s spectrum can be resolved into different contributions of bound carbon which reflect their local environment. And we have these 4 different carbon atoms. C1, that refer to CC and CH bonds. C2, that refer to CO bonds. C3 that refer to OCO bonds, and so C4 for OC double bond O. So this is for unmodified nanocrystals, and here nanocrystals graft with the aliphatic chains. And so what is really clear on this figure is that after grafting, there is a strong increase in the C1 signal. And so this is really the signature of the grafting of these aliphatic chains. And from this curve, it's possible to determine what is called the surface coverage, which is given by this equation. So AC1M refers to the area of the C1 peak for modified nanocrystals, and this parameter to unmodified nanoparticles or nanocrystals. So this is just a curve that show you the evolution of the degree of substitution that has been determined by elemental analysis, the surface coverage determined by XPS as a function of the number of carbon of the graft chains. So you can see that the degree of substitution decreases. So this is only due to steric hindrance, of course, but the surface coverage increases. So solid-state nuclear magnetic resonance spectroscopy, NMR. So it is a spectroscopic technique which is used to characterize atomic level structure and dynamics in solid materials. So this is the typical NMR, solid-state NMR spectrum of cellulose with different peaks that correspond to the different carbons of the oxygen, which are numbered 1, 2, up to 6. And we can have this different signal which are reported here and that are described here. So each peak refers to one carbon atom, except for this peak, where it is difficult to make a distinct, well, to identify and find these different carbon atoms. So this is an example. So untreated cotton was used and it was grafted with methyl methacrylate with different grafting yield, you can see here. And of course, from the NMR spectra, we can find the signal associated to cellulose, but we have new signal which is associated to the graft chain. I will not detail, but in this case, in the case of methyl methacrylate, we have these different peaks here, which are referred on this molecule, and that can be seen here, which are absent, of course, for unmodified nanocrystals. So Raman spectroscopy can also be used. I'm not really expert in this different technique, but I know more or less how it works. So Raman is a light scattering technique based on the interactions of light with the chemical bonds in a material in which a molecule scatters incident light from a high-intensity laser light source. So in this case, we have different spectra. There is no, This is for unmodified cotton fibers, where we have some specific signal of cellulose, including OH, of course. And then after grafting, in this case polystyrene was grafted on the surface of the cotton fibers, we have new signal, which are referred here. And of course, when the grafting efficiency increase, so the highest one is here, we have stronger signal. And in this case, it can be quantified. Thermographic analysis. So it's not really a technique which is used to determine the grafting efficiency. So it's more used to determine the thermal stability of a material. In this experiment, the sample is heat in a given environment. So it can be air, nitrogen, carbon dioxide, helium, argon, etc., at a control rate. So usually we start from room temperature and it is heat up to 600 degrees to completely degrade the material. The change in weight of the material is recorded as a function of temperature, and so we obtain this kind of curve. And in this case, so you have the reference, so it's not very clear, I think it's this signal that refers to unmodified microfibrillate cellulose or cellulose nanofibrils, and these cellulose nanofibrils have been grafted with polycaprolactone with different molecular weight, and so it changed a little bit the signal. So it's not really easy to see from this plot. Usually, the derivative of this signal is used, and by making a zoom on this region, we can see that for graft cellulose nanofibrils, we have a double peak. And of course, the second peak is associated to the graft polycaprolactone chain. And in this study, a curve fitting has been used to estimate at least the amount of graft polymer. So DSC, differential scanning calorimetry, also this technique is not usually used to determine the grafting efficiency. This technique is mainly used to determine the thermal transition, glass transition, crystallization, melting, but in some cases it can be used to, at least to qualitatively see if some molecules have been grafted or not. Just to recall what is this technique, so it consists in measuring as a function of temperature or time, because constant heating rate or cooling rate is applied, and in comparison with an inert reference, So usually this reference is air, there is no transition. The heat which is produced or absorbed during the transition of a material. So you have the equipment here with the reference, the sample, and a heat flow is provided to both the reference and the sample in order to increase the temperature. Of course, if no transition occurs in the material, the same heat flow is provided to the sample and to the reference. And what we measure is the difference in the heat flow, meaning that in this case, if there is no transition, you don't measure anything. But if there is a transition, let's say, for example, a non-endothermic transition in the sample, in this case, it's necessary to provide energy to the sample for the transition to occur. But what is imposed here in DSC experiment is that it's necessary to have always the same temperature at the level of the reference and at the level of the temperature. Meaning that if there is a non-endothermic transition, more energy will be provided to the sample in order to keep the same temperature as the reference and in order to provide energy for the endothermic transition. Of course, we have the opposite for an exothermic transition. So it means that in this experiment, the heat flow, or the difference in heat flow, is plotted as a function of temperature. I tell you, it can be time. But because a constant heating or cooling rate is applied, so it is the same, of course. Usually we use temperature, of course. But isothermal experiment can be performed. So it means that in this case we have time on the x-axis, for example, to follow a chemical reaction. So this parameter is determined, so the difference between the heat flow provided to the sample and the heat flow provided to the reference. Some thermodynamics. The internal energy is given by this equation. We have also the differential enthalpy, which is given by this equation. And in fact, it is equivalent to the heat flow. The reason is that DSC is working at constant pressure. What it means is that here we can report the heat flow or the enthalpy flow. It's exactly the same thing. And it is equivalent to the heat capacity, which is defined by this equation. So it can be written like this. And this parameter, which is the opposite of the heating rate or cooling rate, is constant, meaning that we can also report here the heat capacity. We can use these three parameters: heat flow, enthalpy flow, or heat capacity. So we can determine the transition in a material, and these transitions are of two types: first-order transition, second-order transition. A first-order transition is characterized by a drop in the thermodynamic characteristics such as enthalpy or specific volume. We have a drop in this parameter. Here we have the derivative of the enthalpy because we are determining an enthalpy flow. And of course, if we have a drop in enthalpy, it means that we should have a peak on the derivative. We can observe two types of peak. Usually the endothermic and exothermic direction is referred. Here, in this case, the endothermic direction is up because we have a peak here which is in the exothermic direction. That refers to the crystallization. And here, a peak in the endothermic direction that refers to melting. Melting and crystallization are first-order transition. Now, a second-order transition is characterized by a sharp change in the first derivative of enthalpy, which is the case here. We measure the enthalpy flow, so it's a derivative of the enthalpy, and we have this charge change. So it is the case for glass transition. Glass transition has all the characteristics of a second order transition, but it is not. It is not because to be a transition, it's necessary to pass from one equilibrium state to another equilibrium state. The rubbery state is an equilibrium state. The glassy state is not. So it means that the glass transition has all the characteristics of a second order transition, but it is not. So these are the main transitions that we can determine for a polymer. Now regarding the grafting of molecule, this is the same example as previously. You remember polyethylene glycol has been grafted on the surface of starch nanocrystals with a good affinity of the graft chain for the surface of the nanocrystals, meaning that we have something like this because of the oxygen atom. And in the case of the stearates, there is no affinity, and we have a brush-like structure. You remember that for this sample previously, in this case, a diffraction peak was observed that corresponds to polyethylene. Short chain, of course, polyethylene. When performing DSC experiment for unmodified nanocrystals, we have this signal, modified with polyethylene glycol this signal, and in the case of the stearate graft nanoparticles or nanocrystals, we have a peak. So it is not referred, but the endothermic direction is down. So meaning that it's a melting peak. It corresponds to the melting of this crystalline brush-like structure with graft chains which are long enough to crystallize. So of course the structure is similar to polyethylene, but you can see that the melting point is lower than for polyethylene. In the case of low density polyethylene, the temperature, the melting temperature is around 105 degrees, and for high density polyethylene, it is more 140 degrees. The reason for this low melting point of the graft structure is that, of course, the size of the crystals is small, because it just consists on 16 carbon atoms. And so remember that the melting point is representative of the size of the crystals. There is one equation, so I don't remember exactly this equation, but it is the Debye equation that link the melting point to the size of the crystal. So, it's an indication that, of course, we have effectively graphed molecule on the surface. This is another example in which polycaprolactone, so it's the same as previously also, polycaprolactone has been grafted on the surface of cellulose nanocrystals using a grafting on two approach. So the melting peaks are not very well defined, but they are, I don't have the DSC for the unmodified nanocrystals, but there is no peak in this case. And so it is associated to the grafting of this molecule. And in this case, remember, I think the molecular weight of graft polycaprolactone was something like 10,000 and 40,000 gram per mole, so it's quite long molecule. What we can expect, and we observe this, I will not show here, but we have a transcrystallization. Crystallization between the graft polycaprolactone molecule and polycaprolactone molecules from the matrix, which lead, of course, to strong interaction at the interface. So this is maybe a little bit specific. It is the end functionalization of cellulose nanocrystals and cellulose nanofibrils. So you remember that in the cellulose macromolecule, the two ends are not equivalent. there is a non-reducing end and a reducing end. And it's possible to specifically graft the reducing end following some chemistry that I will not detail here because I'm not expert in this. I know that it's called, where is it? Thiolation. Yes, I'm correct. Thiolation. So in fact, this grafting at the end of the nanofibrils or nanocrystal can be interesting in some case because remember that we have seen that the high mechanical properties of cellulose-based nanocomposite is due to this percolation effect, meaning that the nanocrystals can interact through hydrogen bonding. When chemically modifying the surface of the nanocrystals, of course, we cannot form this percolating network. But if the chemical modification is performed at the end of the nanoparticles, we keep the edge group from the surface to interact and to form a percolating network. So after chemical modification of the reducing end of the nanoparticles, it's possible to, think somewhere, yes, to functionalize this function with silver nanoparticles at the reducing end. And we can then observe by a microscopy these nanoparticles. So this is for unmodified cellulose nanofibrils. And for modified nanofibrils at the end, following two different strategies, and we can see this black dot that refer to the graft silver nanoparticle. So this is an indication of the effective functionalization of the nanocrystals. So, it was shorter than other lecture. Some conclusion. Before characterization, to evaluate the grafting efficiency, it's necessary to perform an extensive washing, surface extraction, or solubilization certification to remove ungrafted species. It is also important to ensure that grafting conditions are mild enough not to solubilize the cellulose. We should keep the crystalline structure of cellulose. We just want to modify the surface. Several techniques are generally used to evidence the surface modification of fibers or nanoparticles simultaneously, meaning that usually several techniques are used. Even if evidence can be provided by one technique, in general, several techniques are used. This technique reveals the hydrophobization of the surface of the fibers and nanoparticles, and also with some of this technique, it's possible to determine, or at least to estimate, the degree of grafting or the degree of substitution. Do you have any question?
So thank you so much for the presentation. So the grafting, the degree of the grafting, generally little more easier for thermoplastic with nanocellulose, like PLA is basically can undergo melting, and then we can get something good data from DSC or something like that.
From DSC, it's difficult to quantify because you know from DSC we can maybe observe a melting point if the polymer, the graft polymer, can crystallize, but it's very difficult to quantify, to determine the degree of substitution. Okay. To determine the degree of substitution, usually elemental analysis can be used, or solid-state NMR, sorry, RMN is in French. Solid-state NMR can be used. These are the main techniques. Also from infrared, it's very difficult to quantify the degree of substitution. The reason is that by infrared, you have access of the whole sample, including the core of the fiber or the core of the nanoparticles, which is not graphed. Meaning that grafting, because it is not just at the surface, so it's difficult to quantify.
Okay.
From XPS also we can quantify.
Okay. Thank you. And if that is grafting techniques being used for even thermoset polymers also, right?
Yes, 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 yes.
So there also maybe I think again this kind of tech.
Of course, yes, of course. Because here we don't care about the matrix.
Yeah.
This characterization only refer to the modified fibers or modified nanoparticles,
Okay. That's all.
not the matrix.
Thank you. Thank you.
I have one doubt. When nature make these fibers or cellulose nanocrystal,
Yeah.
will it have a very high PDI value,
Very high, sorry.
polydispersity index?
Oh, yes, 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 yes. You mean of the cellulose chain?
Yes.
Yes, yes, yes. And we can see this, so I don't have here, but when I show TM image of cellulose nanocrystals, there is a very broad distribution in length. Meaning that, you know, these nanocrystals come from the fibrils, which is a kind of string of alternating amorphous and crystalline domains. So I don't know what happened during the biosynthesis of cellulose, but the enzymes so produce cellulose. They produce crystalline cellulose, and sometimes, I don't know what happened, some amorphous, but it's more or less random. So it's not perfectly organized.
Thank you.
Yes.
I joined slightly late, therefore I do not know whether I missed it. Present, how normally what is the route to calculate percentage of grafting and how it can be improved?
Yes. In fact, it is mainly determined from elemental analysis, which is, it's necessary to use an equation. I didn't detail the equation, but I gave it. Yes, it's this one. That gives a degree of substitution, so it's necessary to have the relative carbon content in the sample, which is determined, of course, by elemental analysis. So it's necessary to know the carbon molecular weight of one anhydroglucose unite. So this is well known, of course. The mass of anhydroglucose unite, which is known. The mass of the graft molecule that can be determined by gravimetry, for example, and the carbon mass of the graft molecule. So we know, of course, the molecule which is graft, meaning that we know this parameter. And this is the main technique which is used to really quantify the number of OH groups that have been replaced by other molecules. It's a quite easy technique. It's not available in, for example, in Grenoble, we don't have this elemental analysis. We send the sample to, there is a lab which is specialized in this, and they receive sample from the whole France and they perform the experiment. Yes, sorry.
Normally grafting enhances the interfacial tension because at the interface there will be more anchoring between the substrate and the cellulose fibers. So how we can, what are the strategies to evaluate the interfacial strength after doing a grafting protocol?
What do you mean by the interfacial
We have
structure?
cellulose surface is grafted.
Yes.
So that most probably may be introducing more polar groups, and that will be getting anchored onto the polymer so that the binding between the polymer and the cellulose is elevated.
Yes, so you mean that the polar component of the surface tension is lower?
So
No.
therefore, when the binding increases between the fiber and the matrix, binding increases, interfacial strength increases.
Yes.
So how we can quantify? Do you have
To quantify, I show, I don't remember if it was before or after. It was maybe before. One quantification is from the contact angle measurement. Because, so you know that if the surface, if you put a droplet of water on the surface of a polar surface, so the contact angle, a polar surface, the contact angle is low. On the contrary, if the surface is more hydrophobic, it increases the contact angle. And so I show this approach, which is the Owens-Wendt approach.
Accommodation calculation. So this is beautiful, beautiful calculation.
Yes. And so we can clearly see, which was here, so it was for cellulose nanoparticles, unmodified and graphed, and so there is a very clear decrease of the polar component of the surface tension of cellulose. Yes, and this is a quantification.
Sir, my question may be silly, but in most of the TG instruments, I have seen that we will be using inert atmosphere. But in your one of the slides, it was mentioned that we can use air as
Yes.
atmosphere itself.
Yes,
So,
usually nitrogen atmosphere is used, but we can use also air atmosphere. What is important is that if you want to compare sample between your sample with other sample, it's necessary to have the same atmosphere, of course.
my question is after filling, after incorporating filler into the matrix, we don't know whether it will be, the ignition temperature of the composite is within the range which we are going to apply, the temperature range or not. So once we perform the TGA analysis, if the ignition temperature of the composite is within the temperature range, that it will burn out. So do we need to go in a certain characteristic techniques, like first we need to perform a DSC, then TGA, or such kind of things?
No, because it's completely different experiment. TGA, you determine the thermal degradation temperature. And you can determine also what is called what is the name? The remaining weight of the sample. Residue, yes, the residue. In DSC, it's completely different. You determine the transition.
So
you cannot
predict the ignition temperature
No.
of the composite.
No.
The thing which you said is residue.
Residue, yes. After the degradation, I don't know if we see here in the curves that I show. After the degradation process, I think it was before or after, I don't remember. No, it was after. Yes. You see, after the degradation, this weight corresponds to what is called the residue. And so it can give also some information on the material, on the degradation of the material.
Sir, I have one curiosity. In the second last slide, probably I missed out, I'm not sure.
Which slide?
The second last one, 30th.
The second last one.
So there you,
No.
I mean the previous one. N functionalization.
This one?
Yeah, previous one.
Or this one?
Yes. So you wanted to N functionalize because you still want to improve the mechanical properties of it so that percolation happens.
Yes, the objective is to keep intact the OH groups from the surface.
So,
But it
now-
can be used for another reason. But
Okay. Now, my question is, if you want to just N-functionalize, still you have other OH active groups on the polymer chain. So it must be very difficult specifically going to the N-functionalization, right? So you need to do some protection during this.
to avoid to graph the OH group, no. No, because I think, I'm not sure, but it's a different reaction. Meaning that in this case, the OH group from the surface cannot react. Only the end, reducing end of the.
I see, okay.
In this case, no, it's not this case, sorry. was in this case. So it was one of my PhD students, Ge Zhu. He performed this chemical modification to mix the nanofibrils with natural rubber. And in fact, he graphed another, I don't remember what he was chemist, so he can manage. He graphed another molecule at the end of the nanofibrils to cross-link the nanofibrils with the natural rubber.